In the last video, we talked about using trigonometric ratios to find the missing side lengths. In this video, we're going to not only do that, we're also going to look for the missing angle measures using the inverse trigonometric ratios. Before we do that, let's review really quickly what the sine of theta, cosine of theta, and tangent of theta meant. Opposite over hypotenuse refers to sine of theta. Cosine of theta means the side length that is adjacent to the angle is being compared with the hypotenuse, and opposite over adjacent is the ratio called tangent. Now, they do talk about this this abbreviation that might be helpful here. They call it SOHCAHTOA, saying sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. SOHCAHTOA. If that helps you, you can use it. If it just helps you to memorize this left side over here, that's perfectly fine as well. Let's think about this triangle over here. The question says, which angle, angle 1 or angle 2, is A referring to, this A, if cosine of that angle is 0.6? Cosine of this angle refers to adjacent over hypotenuse, right? So if this A we're talking about were to be angle 1, so cosine of angle 1 will be adjacent side, 3.6 over 6, right? Hypotenuse. And cosine of 2, angle 2 will be, seeing from 2, the adjacent side, 4.8 over 6, the hypotenuse. Let's see which one is 0.6, so we know what angle A was all along. So that you can reduce that. I think 0.6 goes in there 6 times on the top and 10 times on the bottom, which we can actually see that's the case, whereas cosine of 2 is actually going to be 8 over 10. So that's going to be 0.8. That's going to be 0.6. That means this angle A that we're looking for was angle 1 after all. Now, you can see how doing this kind of guessing game, right, plugging in the angles and seeing what the ratio actually matches up might get cumbersome. So here is our really powerful but really helpful ratios that we can use, and these are called the inverse trigonometric ratios. Here it is. It says if sine of A, if the ratio of the opposite and the hypotenuse is some number x, that means the inverse of that ratio, the inverse sine of that ratio is the angle measure. You can either look at that, or you can also think about it like this. If you know sine of angle A equals x, we can take the inverse sine of both sides, just like you would take sine of both sides, or just like you would multiply 2 on both sides. If you take the inverse sine, which is an operation, of both sides, then these actually go away, just like you would square a square root, just like you would multiply by reciprocal. These would reduce, and a will be left, and a, the measure of angle A will be simply inverse sine of that ratio from the start. So basically, if you have cosine of some angle being that ratio, if you take the inverse cosine of that ratio, you get the hidden angle measure. Again, tangent of some angle measure equals that ratio. If you take that ratio and take the inverse tangent of it, you'll get to know what that angle measure was all along. Here's an example. Let's have our handy dandy 3, 4, 5 triangle. And this is the angle that we'll talk about. We know sine of A, because it's comparing between opposite and hypotenuse, will be 3 over 5, right? Or 0.6. But let's say if we know that sine of A is 3 over 5, that means if we take the inverse sine of 3 over 5, which will be 36.87, that will be the measure of angle A. Or you might want to look at it like this too. You can say, well, it's really going from here, taking the inverse sine of both sides, which means the measure of angle A is inverse sine of 3 over 5. This is how you parse it out. This is how you go about doing the problem. First, you want to use the given lengths to set up a trigonometric ratios, just like how we did it here. And then you want to solve for the missing side lengths by using sine, cosine, and tangent, just like the last section. But this section, what's new is we're using inverse trigonometric ratios to solve for the angle measures. We're missing this word measures. We're using the inverse to find the angle measures. We're using the regular sine, cosine, and tangent ratios to find the missing side lengths. Let's look at another example. We have a triangle with two known side lengths. We want to figure out what the hypotenuse and the length of the hypotenuse is. We want to know the measure of this angle over here and measure of angle C. Let's jump right into it. Let's figure out the measure of angle A first. The measure of angle A, let's see, if you take this some sort of trig ratio, it's going to be comparing 5 and 7.5, just because we know those measures. Well, compared to A, if you look at it from A, 5 is the opposite and 7.5 is the adjacent, isn't it? So the ratio that compares opposite and adjacent is tangent. So tangent of angle A will be opposite over adjacent. This is a critical piece right here. If tangent of A equals 5 over 7.5, we can take the inverse tangent of both sides and measure of angle A will be inverse tangent of 5 over 7.5, which you can put in just the same way into the calculator. It's just shift tangent. Shift tangent of 5 over 7.5 turns out to be 33.69 degrees. So this is 33.69 degrees, which makes the measure of angle C to be the the complement of that, right? So 90 minus 33.69 equals 56.31 degrees. That was easy. So how do we figure out the length of the hypotenuse? We could use the Pythagorean theorem, but that'd be kind of boring. Let's use one of these angles to actually find out the length of the hypotenuse. Let's try using sine here. If we use sine of A, right, sine of angle A, that would be comparing the opposite side, 5, to the hypotenuse, wouldn't it? The opposite over hypotenuse. And sine of A, sine of 33.69 equals all that, which means AC times sine of 33.69 equals 5 if you multiply AC on both sides. Right here, if you multiply AC on both sides, you have AC times sine of 33.69 equals 5. And if we divide both sides by sine of 33.69, we have actually which turns out to be 5 over 0.55, and that turns out to be 9.01, and that is the length of AC, the hypotenuse. So notice how we're using the inverse trig functions to figure out the angle measures, and we can use a property of the acute angles in a right triangle being complementary, so we figured that out. And then we used sine to figure out the missing side length. Let's look at one more example. This one we have it a little easier. We already know this measure angle A is 32, which means the other one over here, measure angle C, must be the complement. So it's going to be 58 degrees because the complement, they add up to what? They add up to 90. Well, let's figure out what the length of AB and BC are. You might be tempted to use the Pythagorean theorem, which will be nice, but we have two missing side lengths, so we can't really use Pythagorean theorem. But let's use one of the trig ratios. It doesn't matter which angle we choose, but let's just choose A, 32 degrees, and find out what AB is. When you look at from angle A, AB is adjacent, isn't it? And we know, we should probably use the given or the known measure, which happens to be hypotenuse, and is hypotenuse whatever angle you choose. The ratio that we know that compares adjacent to hypotenuse is cosine. So cosine of 32 is AB, the adjacent side, over hypotenuse, 7.4. That means since cosine of 32 is 0.848, AB, when you multiply 7.4 on both sides, will be 6.28. Now let's figure out what BC is. BC, if you look at it from angle A, let's just use angle A again. Doesn't matter, you could use angle C if you want. You just have to adjust cosine and sine because the opposite and the adjacent would change. If you look at it from angle A, BC is an opposite, right? It'll still be hypotenuse. So sine of 32 degrees will be whatever BC is over hypotenuse, 7.4. Sine of 32 happens to be 0.53. And if you multiply 7.4 on both sides, BC ends up equaling 3.92. And that's how you solve for right triangles. Let's do, here we have similar situation as the first example, but here we're missing measure angle y, measure angle z, and the length of the hypotenuse. Let's figure out the measure of angle y first. Compared to, when you look at it from angle y, 8.6 is the opposite, right? And 11 is adjacent. So first figure that out, and then say, well, the ratio that compares those two is tangent. So tangent of y equals 8.6 over 11. So in order to find out what the measure of y is, we don't want this tangent, right? So we want to take the inverse tangent of both sides. Both sides. Did I mention both sides? Great. And then y then equals inverse tangent of 8.6 over 11, which you can put right into the calculator. Make sure you're in degrees. And y turns out to be 38.02. 38.02, which means the measure of angle z is 90 minus 38.02, which happens to be 51.98. And again, you can use the Pythagorean theorem to figure out the length of the hypotenuse, but what's the fun in that, because we've done enough practice with that. Let's use one of the trig ratios to figure out the hypotenuse. Well, you know you have to use either sine or cosine because they both involve the length of the hypotenuse. So if we use angle y, and sine or cosine, it doesn't really matter. We know pretty much everything else. So let's just use sine. Sine of y will be comparing between opposite, which in this case is 8.6, over yz. We also know what sine of y is. Sine of, well, we know what y is. Y is 38.02 equals 8.6 over yz. We can multiply both sides by yz. So yz times this interesting number equals 8.6, which means yz is 8.6 over that interesting number, which happens to be sine of 38.02 happens to be 0.616. So 8.6 divided by that will be 13.96. And that is the length of the hypotenuse. Again, when you look at a triangle, try to see which ones are known and which ones are unknown. Try to set up a trigonometric ratio with the known values. So we started right away with 8.6 and 11. We're like, oh, those are opposite and adjacent when you look at it from angle y. So set up the trigonometric ratio and then solve for it. If you want to solve for an angle, you will have to use inverse trig ratio, like inverse tangent or inverse sine, inverse cosine. But then if you know the angle value but want to figure out the side lengths, you just have to use sine, cosine, or tangent. I hope that helps. Look in the book for more examples, and good luck.